Hello guys, we are back with our next lecture. In this lecture, let us go through the next topic, that is a decision properties, guys. Okay, so in the last lecture we discussed about Mealy and Mooley machines and all those things, right? Yes. So in this lecture, let us continue with the decision properties, guys. Okay, so basically what are these decision properties? To be decision properties are what is this decision thing? So basically this particular thing I think we have covered in around 2 subjects till now, right? So we studied this in data structures, we studied this in algorithms according to my knowledge. I'm not 100% sure, but in algorithms we have studied for this for sure, guys. Okay, so this is nothing but so if we divide problems into 2 parts, so problems could be of a solvable nature and the other type is unsolvable, right? Yes. So what do I mean by solvable, guys? Means there exists a solution, right? Yes. So what do I mean by unsolvable? So do I mean it is a solution doesn't exist? That is wrong. Basically solvable means it includes solutions which exist as well as solutions which doesn't exist. Okay. Whereas unsolvable means till now they are not solved. So till now we are not able to justify that whether it is possible or not. Got it? Yes. So the best example for this is so when it comes to solvable, okay, so the solution is okay, so the solution exists. So assume that you want to do binary search, binary BST. So if you want to build binary search tree, so those type of things are possible, right, in reality. So for them solutions exist. So that is the reason why we were able to give time, right? It will take big O of n time, it will take big log n time, in that way. So that is nothing but solution exists. What about solution doesn't exist? So there could be some problems which can never be solved, right? You're 100% sure about them. So those comes under this solutions doesn't exist. And what about unsolvable? So basically unsolvable means we are not saying that solution will exist, we are not saying that solution will not exist, but we are in a dilemma that it might be possible in the future. So that is unsolvable. So can you say that can we do time travel? The answer is maybe in future, we don't know now. So those type of things comes under this unsolvable, guys. Got it? Yes. So when we are going in detail about this solvable also, there are 2 paths, guys. Okay, so the first path is a procedure and the second path is algorithm. So when it comes to procedure, here we don't know the exact code how you are going to write, but we know that it is possible. So those comes under the here, guys. So procedure, we know steps but cannot specify time. Undecidable. So basically undecidable and decidability. So these are more popular terms, right? Yes. So when it comes to undecidability means we are not able to justify in some time. So basically it will take this much time, it will take this much time, like that. So we are able to say these steps. So following these steps it is possible. So the best example for this will be isomorphism, guys. So if you recall in discrete mathematics we have studied the concept of isomorphism, right? So what is isomorphism? It is nothing but how can we say 2 graphs are same or not, right? Yes. So when it comes to here, okay, so when it comes to this undecidable, so can you say whether 2 graphs are isomorphism in a specific time? No. So there are various steps. It's a trial and error method, right? Yes. And when it comes to algorithmic method, so here we have a particular code and we can say that whether it will take polynomial time or non-polynomial time. Got it? Yes. So these are nothing but the P type problems. These are nothing but the NP class. So P class and NP class. So this is indirectly about decision and all those things, right? Yes. Decidability and all those things, right? Yes. So now I hope everyone got a clear idea about this whole flow, right? Yes. The only reason why I discussed about this flow is for you to understand the concept about these solvable and unsolvable and all those things, right? Yes. Okay. So now let us continue with what are the decision properties followed by regular language or regular grammar, and similarly what are the closure properties which are followed by regular language, guys. So these are the 2 things which we will be discussing, and to be clear these already I have a table, guys. So basically I got that table from our educator. So basically it was a clear table, guys. You can find everything in it. So basically I'll be showing you that table in our future lectures, so don't worry. Okay, yes. And I'll be saying you some tricks to remember them also, guys, like how you can remember them in examination and how you can easily keep this answer correct. So basically every year almost, guys, you can say like in any one of the set you will get compulsory 1 question from this topic. Okay, yes. Okay, so now let us continue and discuss about decision properties, guys. Okay, so regular language follows 6 decision properties. So the first is emptiness, non-emptiness, finiteness, infiniteness, membership, equality. So these are the 6 different decision properties. Okay, so when it comes to emptiness and non-emptiness, how can we say that a particular regular language or regular grammar is empty or non-empty, guys? So based on its generating power, right? So if it is generating of at least one item, it is non-empty. If it is not generating anything, it is empty, right? Yes. So step one is what, guys? Select the state that cannot be reached from the initial state and delete them. Those are nothing but unreachable states. Okay, similarly, if the resulting machine contains at least one final state, so then the final automata accepts a non-empty language. Okay, so if the resulting machine is free from a final state, then it is an empty language. So basically, instead of talking in my way, in books we will find in this way, guys. So first of all, you will remove all unwanted and all those states, unnecessary states, which are not reachable. So not reachable means there is no input for that state. Okay, yes. So you will remove all those states, and what is the final diagram which we got? So in that, if a final state is there, it will accept something, right? Yes. So that is the reason why it is a non-empty, and if there is no final state, it is empty. Got it? Yes. Similarly, moving on to finite and infinite. Okay, so the step 1, so everywhere the step 1 will be same, guys. So remove unreachable states. Step 2 is remove dead states. Step 3 is if the resulting machine contains loop or cycle, then the finite automata accepts infinite language. If it is not having any loop or anything, then it is a finite, right? Yes. Okay, so moving on to membership. So in simple words, membership is nothing but acceptance, guys. So can we say give a particular string, and can we say that this string is accepted by this machine? Yes. So that is possible, and that is the thing which DFAs and all those things do, right? Yes. So membership is followed by finite automata, and similarly we can say also equality, right? So if a particular thing is given, like a particular regular language is given, and one more particular regular language is given, so the first step will be draw the finite state machine for it. So once the finite state machine is done, then you will be drawing the minimal finite state machine, that is a MFA, minimum finite state machine, or minimum DFA you can say. So if both of these are equal, at the end you can conclude that both of them are equal, right? So both the regular languages are also equal. So to be clear, if you recall, I told one important thing. So any regular language or any finite automata you are drawing, it is going to have only a single minimum finite state machine, guys. Got it? Yes. So it will always be unique. So that is the reason why it will directly match, and you can conclude that whether they are equal or not. Got it? Yes. So these are the 6 different decision properties with respect to regular language: emptiness, non-emptiness, finite, infinite, membership, and equality. And it follows all of them. Okay? Yes. And moving on to closure property. Okay? So closure properties for regular language. Okay? Okay. So regular language follows a clean closure, follows a positive closure, follows a complement, follows a reverse operation, follows a operator prefix operation. Okay, follows a symmetrical difference. I think it will not follow symmetrical difference. It follows a suffix operation. It follows a concatenation. It follows a union. It follows intersection. It follows set difference. Okay, yes. Okay, so it follows almost everything, right? Yes. So just to give me a second, guys. If possible, I'll be bringing the table, or I'll be showing you in the next lectures. Okay, just to give me a second. Okay, so I think that director table is missing, guys. So this is my book which I have written in the last year. Okay, yes. So basically regular language will follow everything, whereas deterministic PDA will not follow reverse operation, union, intersection, and clean closure. So in this way it is available. So this is with respect to closure properties. And similarly, when it comes to decidable properties, so it's clearly you can remember it, guys. I have written a trick also. So anyway, we'll be discussing whenever it's needed, guys. At the end of the whole subject, mostly I'll be covering this thing. Okay. Yes. So now you understood, right? So directly from this all things, you can expect one question, guys. Okay. Yes. So now I hope everyone got a clear idea with respect to this decision property and closure properties, right? Yes. Okay. So now I hope everyone got a clear idea on this. So in the next lecture, we'll be discussing about the last topic with respect to this. That is a pumping lemma, guys. So what is the main reason why we study pumping lemma is to prove that a particular non-regular language is a non-regular, to prove that we use pumping lemma, guys. Okay. Yes. So that the thing which I told you was really funny, but we'll be discussing about that importance of pumping lemma in the next lecture. Okay. Yes. So let us meet in the next lecture. Thank you. Thanks for watching. Like, share, and subscribe for more awesome videos like this. Thank you.